Welcome! In this session, we'll dive into LeetCode problem number 848, shifting letters. Together, we'll break down the problem, analyze possible approaches, and work toward an efficient solution. Let's get started. In this problem, we are given a string S that consists of lowercase English letters, and an array shifts which has the same length as the string. The goal is to shift each character in the string to the right by a certain number of positions, as specified in the shifts array. To clarify, a shift means that each letter moves forward in the alphabet. A becomes B, B becomes C, and so on. When we reach Z, it wraps around back to A. For example, shifting Z by one position results in A. The task is to return the final string after applying all these shifts to the characters in S. The input consists of the string S and the array shifts. The constraints tell us that the length of S can be up to 100,000. And each value in shifts can go up to a billion. This means we need an efficient solution to handle large inputs. For the output, we return the transformed version of the string after applying all the shifts. To understand this problem better, let's look at an example. Suppose the input string is S equals ABC and the shifts array is 3, 5, 9. The output is RPL. Here's how we calculate it. Starting from the rightmost character, we compute the total shifts needed for each letter. For the last letter C, which is at index 2, we apply 9 shifts. Shifting C forward by 9 positions gives us L. For the letter B, at index 1, we add its shift value, 5, to the shifts already applied to C, which is 9. That makes 14 shifts in total for B. Shifting B forward by 14 positions gives us P. Finally, for the first letter A, at index 0, we sum up all the shift values, 3 plus 5 plus 9, which equals 17. Shifting A forward by 17 positions results in R. Combining these transformations, the final string becomes RPL. Here's another example to further illustrate the process. Consider the input S equals AAA in the shifts array, 1, 2, 3. The output is GFD. Let's break it down. For the last letter A at index 2, the shift value is 3. Shifting A forward by 3 positions gives us D. For the second to last letter A at index 1, we add its shift value, 2, to the shifts already applied to the last letter, which is 3. This totals 5 shifts for the second letter. Shifting A forward by 5 positions gives us F. For the first letter A at index 0, we sum all the shift values, 1 plus 2 plus 3, which equals 6. Shifting A forward by 6 positions results in G. Putting these together, the final string is GFD. This example highlights the importance of calculating the cumulative shifts starting from the rightmost character. Now, let's consider a few edge cases to ensure the solution works for all scenarios. First, if the string contains only one character, like S equals Z with shifts equals 26, the output remains Z because a full cycle of 26 shifts brings Z back to itself. Next, if all the values in the shifts array are 0, such as S equals ABC and shifts equals 0, 0, 0, the output is the same as the input string, ABC, since no shifts are applied. Finally, when the shifts are very large, for example, S equals A and shifts equals 10 to the power of 9, the result is still A. This is because shifting by a billion is equivalent to shifting by 10⁻9% 26 equals 6, as the alphabet is cyclic with 26 letters. These cases demonstrate how the problem scales and highlights the need to optimize for efficiency. To tackle the problem of shifting letters, we first consider the brute force approach. This method is straightforward. For each character in the string, we apply the corresponding number of shifts from the shifts array. The shift operation involves adjusting the ASCII value of the character and wrapping around if it exceeds Z. While this method is easy to understand and implement, it comes with notable inefficiencies. Specifically, the time complexity is O(n squared), because for every character, we repeatedly calculate the cumulative sum of shifts. This redundancy makes the approach unsuitable for large inputs, as it becomes computationally expensive. The key limitation here is that it processes the same shift values multiple times, leading to wasted effort and slower performance on larger strings. Now, to improve on the brute force approach, we turn to an optimized strategy using a cumulative sum. The key idea is to pre-process the shifts array by calculating the total shifts for each character in a single backward pass. This eliminates redundant recalculations while maintaining correctness. One important observation is that shifting a character multiple times is mathematically equivalent to applying the sum of all relevant shifts. Additionally, since the alphabet has 26 letters, we can use modular arithmetic to simplify the computation, as a shift by 26 or any multiple of 26 has no effect. To implement this, we initialize a variable total underscore shifts to 0, traverse the shifts array from end to beginning, and maintain a running total of shifts. For each character, we apply the pre-computed shifts modulo 26 and construct the final string efficiently. This way, we ensure that the solution is both faster and more scalable. In terms of complexity, the optimized approach offers significant improvements. The time complexity is O(n), where n is the length of the string. This is because we only traverse the shifts array once and process each character in the string once. The space complexity is O(1), as we only use a few additional variables for computations and do not rely on extra data structures. This makes the approach highly space efficient. By choosing the cumulative sum strategy, we balance efficiency with simplicity. Unlike the brute force method, which is more intuitive but computationally expensive, the optimized approach reduces runtime complexity while remaining easy to implement. The backward traversal and modular arithmetic are key to its efficiency. The breakthrough here was recognizing that the shifts are cumulative and can be pre-computed, which avoids repetitive calculations and drastically improves performance. In conclusion, the optimized cumulative sum approach is the most practical and scalable solution for the shifting letters problem. By pre-processing the shifts with a backward traversal and leveraging modular arithmetic, we achieve a balance of efficiency and simplicity. This strategy eliminates redundancy, minimizes operations, and handles larger inputs effectively, making it ideal for competitive programming and real-world applications. In this problem, we need to transform a string S based on a series of shifts provided in an array. Each character in the string will be shifted forward in the alphabet by a specific number of positions, as indicated by the corresponding value in the shifts array. Our goal is to apply all these shifts sufficiently and generate the final modified string. To achieve this, we start by parsing the inputs, ensuring the string S contains only lowercase letters and that the shifts array has the same length as the string. Next, we move to the key optimization step. Instead of applying the shifts directly, which could lead to redundant computations, we pre-compute the cumulative shifts. By traversing the shifts array in reverse order, we can accumulate the shifts progressively. This is tracked using a variable called cumulative_shift, which is updated at each step by adding the current shift value. To keep numbers manageable, we apply modulo 26 to the cumulative shift at each step, ensuring it remains within the bounds of the alphabet. This pre-computation step significantly speeds up the process of applying the shifts later on by consolidating the necessary adjustments for each character ahead of time. Once we have the cumulative shifts ready, we can proceed to modify the string. Since Python strings are immutable, we use a list called result to store the updated characters as we process them. We iterate through the string S from left to right, and for each character, we retrieve the corresponding shift value from the shifts array. To apply the shift, we first convert the character to its ASCII representation using the ORD function. Then, we calculate its new position in the alphabet by adding the shift value and applying modulo 26 to handle wraparound cases, such as shifting past Z. After determining the new position, we convert it back to a character using the CHR function and append it to the result list. Finally, we combine all the modified characters in the result list into a single string using the join method, which becomes the transformed version of the input string. This approach ensures that the shifts are applied efficiently and that the final output is produced in linear time. This algorithm relies on several key insights to achieve its efficiency. First, the cumulative shifts optimization is crucial. By pre-computing the total shift for each character in reverse order, we avoid redundant calculations and reduce the overall time complexity to O(n). Second, the use of modulo 26 ensures that shifts remain within the bounds of the alphabet, which is particularly important for handling wraparound cases like shifting Z forward by 1 to reach A. Third, the algorithm is designed to be space efficient. By reusing the shifts array to store cumulative shifts, we eliminate the need for additional memory to track these values. Meanwhile, using a list to build the result allows for efficient appending of characters, ensuring that we don't incur unnecessary overhead. Together, these optimizations make the algorithm both time and space efficient, enabling it to handle large inputs gracefully. The choice of data structures, such as arrays for cumulative shifts and a list for constructing the result, further supports this efficiency by keeping operations simple and predictable. Analyzing the complexity of this approach, we see that it is highly efficient. The time complexity is O(n), where n is the length of the string s. This arises because we perform a single pass to compute the cumulative shifts and another pass to apply those shifts to the string. The space complexity is also O(n), which accounts for the result list used to store the modified characters. This is the minimal space required to produce the final output, as we need to store the transformed string somewhere. The algorithm also handles several edge cases effectively. If the input string is empty, we can immediately return an empty string without performing any computations. For cases where all shift values are 0, the output remains identical to the input, as no modifications are needed. When dealing with large shift values, the modulo 26 operation ensures that the calculations remain within the bounds of the alphabet. Lastly, the algorithm gracefully handles single character strings, applying the shift in a single step. These considerations ensure robustness across a wide range of input scenarios. Let's see how the algorithm works with a concrete example. Suppose the input string is s equals abc and the shifts array is 3, 5, 9. First, we calculate the cumulative shifts by traversing the shifts array from right to left. Starting with the rightmost value, we compute the reverse cumulative sum. The last value remains 9, the second becomes 5 plus 9 is equal to 14, and the first remains 3. After applying modulo 26, the cumulative shifts array becomes 3, 14, 9. Now, we apply these shifts to the string s. For the first character a, shifting by 3 results in d. For the second character b, shifting by 14 results in p. Finally, for the third character c, shifting by 9 results in l. Combining these transformed characters gives us the final string, which is dpl. This step-by-step execution demonstrates how the algorithm efficiently applies the shifts to produce the desired output. This implementation solves the shifting letters problem efficiently using a reverse cumulative sum approach. Here's a step-by-step breakdown. 1. Input parsing. The function takes two inputs, s, a lowercase alphabetical string, and shifts, a list of integers representing the shift values for each character in s. 2. Cumulative shifts calculation. To optimize the shifting process, we compute the cumulative sum of the shifts array in reverse. At every index I, from right to left, we add the shift value at the next position, shifts I plus 1, to the current value, shifts I. This ensures that each position in shifts holds the total shift value for all subsequent characters, modulo 26, since there are 26 letters in the alphabet. 3. Character shifting. Once we have the cumulative shifts, we iterate through the string s. For each character s, I, we calculate its new shifted position using modular arithmetic. The formula, ord, s, I, ord, plus shifts, I, %26 computes the new position in the alphabet, and chr, plus ord, converts it back to a character. This ensures wraparound behavior when shifts exceed 26. For result construction, the resulting characters are appended to the result list, which is joined into a string at the end and returned. This solution efficiently handles large inputs because the cumulative sum calculation and character shifting both run in O(n) time. Edge cases, such as small strings or large shift values, are naturally handled by the modular arithmetic and cumulative sum logic. This is the Java implementation of the shifting letters problem, directly mirroring the logic of the provided Python solution. The implementation calculates cumulative shifts in reverse order and shifts each character in the string accordingly. Key differences include the use of Java's char type for character manipulation and a string builder for efficient string concatenation. The functionality is equivalent to the Python version, ensuring the same results. Let's begin with the first example where the input string is ABC and the shifts array is 3, 5, 9. The goal is to shift each character in the string based on the corresponding value in the shifts array, but with a cumulative effect. To do this, we first calculate cumulative shifts by processing the shifts array in reverse order. Starting with the initial array 3, 5, 9, we update shifts 1 by adding shifts 2 modulo 26, which results in 14. Then, shifts 0 is updated by adding shifts 1 modulo 26, giving us 17. The final cumulative shifts array becomes 17, 14, 9. These values now represent the total shifts that each character in the string will undergo, taking into account all subsequent shifts. Now that we have the cumulative shifts, we apply them to each character in the string ABC. Starting with the first character, its ASCII value is 97. We calculate the new position by adding the shift value of 17 and taking modulo 26, which gives 17. Converting this back to a character, we get R, and our result list becomes R. Next, for the character B, its ASCII value is 98. Adding the cumulative shift of 14 gives a new position of 15 modulo 26, which corresponds to the character P. The result list is now R, P. Finally, for C, with an ASCII value of 99, adding the shift of 9 results in 11 modulo 26, giving us L. This makes the result list R, P, L. Joining these characters together, the final output string is RPL. For the second example, the input string is XYZ with a shifts array of 1, 2, 3. We start by calculating the cumulative shifts. Initially, the array is 1, 2, 3. We update shifts 1 by adding shifts 2 modulo 26, which results in 5. Then, shifts 0 is updated by adding shifts 1 modulo 26, giving us 6. The final cumulative shifts array becomes 6, 5, 3. Now, we apply these shifts to the string. For the first character, X, the ASCII value is 120. Adding the shift of 6 and taking modulo 26 gives a new position of 3, which corresponds to the character D. The result list becomes D. For the next character, Y, with an ASCII value of 121, adding the shift of 5 gives a new position of 3 modulo 26, which is also D. The result list is now D, D. Finally, for the character Z, its ASCII value is 122. Adding the cumulative shift of 3 results in a new position of 2 modulo 26, which corresponds to the character C. This makes the result list D, D, C. Joining these characters, the final output string for this example is DDC. Moving to the next example, the input string is AAA with shifts 26, 52, 78. First, we calculate the cumulative shifts. Starting with the initial array 26, 52, 78, shifts 1 is updated by adding shifts 2 modulo 26, but since 78 modulo 26 is 0, shifts 1 remains 52. Similarly, shifts 0 is updated by adding shifts 1 modulo 26, and since 52 modulo 26 is also 0, shifts 0 remains 26. The final cumulative shifts array is 26, 52, 78. With the cumulative shifts calculated, we now apply them to the string AAA. For the first character, its ASCII value is 97. Adding the shift of 26 and taking modulo 26 results in 0, which corresponds to A. The result list becomes A. For the next character, adding the shift of 52 modulo 26, which is 0, again results in A, making the list A. Finally, for the last A, adding the shift of 78 modulo 26, which is also 0, keeps it as A. The result list is A. Joining these characters together, the final output string is AAA. The time complexity of the solution is determined by two main components, the cumulative shifts calculation and the character shifting process. To start, the cumulative shifts are calculated by modifying the shifts array in reverse order. Specifically, for each index I, we add the value of shifts, I plus 1% 26 to shifts, I. This operation is performed in a single pass through the array, requiring O(n) time. Next, during the forward pass, each character in the string is shifted based on the pre-computed cumulative shifts. For each character, a constant time arithmetic operation determines its new value, and this process is repeated for all n characters in the string. Since both the reverse and forward passes iterate through the data sequentially, the total time complexity becomes O(n) plus O(n), which simplifies to O(n). Now, let's discuss the space complexity. The solution begins with the input string S and the shifts array, but these are pre-existing inputs and do not require additional memory allocation. Importantly, the cumulative shifts are calculated in place by modifying the shifts array directly. This approach avoids the need for any extra data structure, contributing no additional space cost. However, we do allocate a result list of size n to store the transformed characters before joining them into the final string. This allocation accounts for an O(n) space requirement. Aside from this, only a few temporary variables are used, which have negligible O(1) space usage. Thus, the overall space complexity of the algorithm is O(n), driven primarily by the result list. Comparing this optimized solution to a naive approach highlights its efficiency. A naive method would involve recalculating the cumulative shifts for each character in the string, resulting in nested iterations. This leads to a time complexity of O(n squared), as each character's shift would require processing all prior shifts. In contrast, the optimized solution precomputes the cumulative shifts in a single reverse pass, eliminating redundant calculations and achieving a linear time complexity of O(n). The space complexity remains O(n) in both approaches due to the need to store the result. Furthermore, the best, average, and worst-case time complexities of the optimized algorithm are all O(n), as the entire input string and shifts array are always processed linearly, regardless of the input distribution. In conclusion, this optimized solution is highly efficient, with linear time and space complexities, making it well-suited for handling large inputs while significantly outperforming the naive approach. Let's start with some common mistakes to watch out for in this problem. One frequent issue is misunderstanding how to accumulate shifts. Remember, the shifts are applied cumulatively from right to left, meaning the total shift for a character includes all the shifts to its right, not just the immediate one. Another common pitfall is performing the modulo operation incorrectly. Since the alphabet is cyclic with 26 letters, you need to ensure that the modulo operation wraps around properly to avoid incorrect transformations. Inefficient brute force implementations are also a major concern. If you apply shifts one by one in a loop for each character, it could result in an O(n squared) time complexity, which doesn't scale well for larger inputs. Additionally, handling negative shifts improperly can be tricky. For example, if you encounter a negative shift, you should normalize it by adding 26 after applying the modulo. Lastly, don't overlook edge cases. What happens if the input string is empty, the shifts array has only one element, or your string contains non-alphabetic characters? Always validate and define behavior for these scenarios to ensure robustness. Now let's focus on some key insights to keep in mind during interviews. Efficiency is paramount, especially for problems like this. While a naive O(n squared) solution might pass for small test cases, it won't hold up under larger constraints. That's why pre-processing the shifts array to calculate cumulative shifts in O(n) is essential. Recognizing patterns in circular arrays is another valuable skill. Since the alphabet behaves cyclically, you'll often encounter problems that rely on modulo arithmetic. Being able to quickly identify and apply this pattern can give you an edge. When discussing your solution, it's important to explain the trade-offs. For example, highlight how pre-processing the shifts reduces time complexity compared to a brute force approach. Finally, always emphasize the importance of test cases during interviews. Bring up edge cases like empty strings, all zero shifts, or the largest possible constraints. This demonstrates not only your thoroughness but also your ability to think critically about problem scenarios. There are also related problems that can help deepen your understanding of these concepts. The most direct variation is, of course, LeetCode 848 itself, which focuses on cumulative shifts in a string. Another relevant problem is LeetCode 238, product of array except self, which involves pre-processing using prefix and suffix products to achieve efficiency. LeetCode 189, rotate array, and LeetCode 796, rotate string, are also closely related. Both of these problems deal with cyclic behavior, whether through array rotations or string rotations, and they require a solid grasp of modulo arithmetic and cyclic patterns. Exploring these problems can help you see how these techniques apply across different contexts. Finally, let's look at some alternative approaches that can optimize your solution further. One effective technique is cumulative shift preprocessing. Instead of applying shifts one at a time, preprocess the shifts array from right to left to compute the cumulative shifts for each character, reducing the time complexity to O(n). Modulo arithmetic is another critical optimization. By normalizing shifts with modulo 26, you can handle cyclic behavior efficiently and avoid unnecessary computations. If space usage is a concern, consider a space-optimized approach. Instead of creating a new string, modify the original string in place, which can reduce auxiliary space from O(n) to O(1). For more complex scenarios, like when the shifts array needs dynamic updates, advanced data structures like binary index trees or segment trees can be invaluable. While these require a deeper understanding, they enable efficient handling of dynamic updates and can significantly enhance your solution's flexibility. Great job! We've successfully solved LeetCode problem number 848, shifting letters. We explored efficient algorithms, highlighted the power of prefix sums, and wrapped up with key takeaways. Thanks for watching. Be sure to like, subscribe, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!